Why does the deeper humanity studies the universe, the more despair it seems to feel? Imagine two stars of equal mass, orbiting around a shared center of gravity. Their trajectories are simple and predictable. But once a third body enters the system, everything becomes chaotic, with no discernible pattern at all. This is one of the earliest discovered chaotic systems, the famous three-body problem. And yet, such a seemingly simple problem has the power to prevent humanity from ever fully uncovering the truth of the universe. So what exactly is going on? As early as the 17th century, the renowned physicist Isaac Newton, through his study of forces acting on objects, formulated the famous laws of motion. If an object's mass, initial velocity, initial position, and all the forces acting upon it are known, then we can predict its state of motion at any future moment in time. We can even precisely calculate the orbital paths of systems like the Earth and the Sun. However, when Newton tried to introduce the Moon and form a three-body system, he found that the motion became extraordinarily chaotic. Although this problem remained unsolved throughout his lifetime, it led him to realize that some mysteries of the universe may lie far beyond the limits of human understanding. Later, in 1772, in an effort to solve the three-body problem, the brilliant French mathematician Joseph-Louis Lagrange proposed the restricted three-body model. By assuming one of the three bodies has negligible mass, he simplified the system for analysis and identified 5 special equilibrium points. These are now known as the famous Lagrange points. At certain points, a small object can maintain a stable position relative to two larger bodies and move along with them. For example, the James Webb Space Telescope is positioned near the second Lagrange point of the Earth-Sun system. Although this discovery did not fully solve the three-body problem, it brought hope and new insight into understanding chaotic systems. Meanwhile, the French astronomer Pierre-Simon Laplace firmly believed that the universe operates strictly under Newton's laws. From this, he derived a deeply unsettling conclusion. Since the universe is composed of fundamental particles, and every particle's state is determined by its previous state, then if we know the exact condition of the universe at a given moment, we can use scientific laws to calculate its future state, again and again, indefinitely. Thus was born Laplace's determinism. It suggests that there exists an all-knowing intelligence, capable of knowing the position and momentum of every particle in the universe at any given moment, as well as all the laws governing the cosmos. With this knowledge, it could predict the entire future of the universe. This hypothetical entity is known as Laplace's Demon. According to determinism, the future of the universe is already fixed. The reason the three-body problem still exists is simply due to our current lack of computational power. This idea shocked the entire astronomical community at the time because it was mathematically and theoretically elegant. Although many later attempted to challenge it, none could fundamentally overturn it. Until 1890, when the French mathematician Henri Poincaré, after countless simulations of the three-body problem, discovered something extraordinary. He found that certain dynamical systems are extremely sensitive to initial conditions. Even the slightest difference at the start can cause a system that once followed simple physical laws to evolve into chaotic and unpredictable motion. He described this as nonlinear complex behavior that cannot be predicted. This discovery stripped Laplace's demon of its power and marked the first time humanity realized that reason is not omnipotent and that the future may inherently be uncertain. This was the beginning of chaos theory. Then came the Lorenz butterfly, which finally dealt the fatal blow to Laplace's all-knowing demon. In 1961, American meteorologist Edward Lorenz was using one of the earliest computers to simulate weather patterns. Because computers at the time were slow, he attempted to save time by restarting a simulation midway instead of running it from the beginning. But to his surprise, the results he obtained were drastically different from the original run. After repeating the experiment many times, Lorenz discovered that in evolving systems, even the tiniest change in initial conditions can lead to massive differences in outcomes. Based on this, he concluded that perfectly accurate weather forecasting is fundamentally impossible. To illustrate this idea, he used a poetic metaphor. The flap of a butterfly's wings in South America could, weeks later, trigger a tornado in Texas. Thus, one of the most important theories in physics, chaos theory, was born. It tells us that in the evolution of all things, there exist both constants and variables, and that precise predictions are impossible using existing formulas and theories. This is why, even with today's immense computational power, weather forecasts beyond a week are barely more reliable than guesswork. Later, through computer simulations, scientists discovered something fascinating. In the three-dimensional phase space of the Lorenz system, each point represents a different trajectory based on initial conditions. Although these trajectories appear complex and unpredictable, they quickly converge into a structured pattern. This is known as the Lorenz attractor, a fractal structure representing the long-term behavior of the system. It reveals the nature of nonlinear dynamics in three-dimensional space. Then, in 1979, the father of fractal geometry, Benoit Mandelbrot, used supercomputers to visualize iterative complex functions. The result was a stunning geometric structure, often referred to as the fingerprint of God, the Mandelbrot set. As an iterative formula, its variables operate within the complex number plane. No matter how much you zoom in, you will always uncover more intricate patterns. These local structures are both different from the whole, and yet strangely similar to it. From that point on, fractal geometry became a crucial tool for understanding chaos, spreading into fields like meteorology, economics, and the life sciences. If you look closely, fractals are everywhere in our world. In nature, the most intuitive fractal structure is branching. From the tangled limbs of trees to coral skeletons, rushing rivers, flashes of lightning, and even shells, snowflakes, leaves, and mountain ranges. These are not coincidences, but inevitable outcomes of natural evolution. It is as if the universe itself is governed by the laws of chaotic fractals. Through simple repetition, it can generate systems of immense complexity. The evolution of life on Earth follows the same principle. Even the intricate network of human blood vessels is shaped by fractal patterns. Scientists have found that when a main blood vessel splits into two branches, the sum of their cross-sectional areas must equal that of the original vessel. Otherwise, fluid dynamics would cause turbulence and backflow, leading to energy loss. Moreover, to efficiently supply the entire body, each branching reduces vessel length, maintaining a ratio where the main vessel is about square root 2 times longer than its branches. This ensures that blood delivers oxygen and nutrients in the most efficient way possible, forming the fractal structure of our vascular system, an optimized solution, refined by nature over billions of years. However, in reality, many factors can disrupt this efficiency. For example, chronic stress can constrict blood vessels, reducing blood flow and leading to issues like hair loss. Hair loss, in turn, can increase psychological stress, creating a vicious cycle. Without timely intervention, The vascular structure within hair follicles can be damaged, eventually leading to irreversible follicle death. Minoxidil 5% foam, approved by both the FDA and national medical guidelines, has a well-established mechanism of action. It helps restore blood flow, allowing hair follicles trapped in chaotic states to return to an orderly growth cycle, ultimately producing thicker, stronger hair. At the same time, fractals are not limited to the microscopic world. Even at the vast scale of the universe, self-similarity still exists. In a universe that is constantly expanding, chaos itself becomes the underlying order. Whether it's the three-body problem or the n-body problem, they all represent the influence of non-linear chaos on celestial dynamics. As a result, we can only rely on mathematical simulations to approximate their behavior, but we can never fully grasp their true underlying laws. And what ultimately prevents us from understanding the universe is precisely this: the inherently unpredictable nature of chaos.